Welcome to AI Frontiers, where we explore the cutting-edge research reshaping our technological future. Today, we're diving deep into the robotics revolution through 9 groundbreaking papers published on September 7, 2025. These studies reveal how artificial intelligence is transforming robotic systems from simple mechanical tools into intelligent agents capable of understanding, adapting, and collaborating in our complex world. Picture this scenario. It's a Tuesday morning, and a robot in a warehouse encounters an unfamiliar screwdriver lying at an odd angle, partially hidden behind other tools. The lighting conditions are completely different from anything in its training data. Yet within seconds, this robot not only understands how to grasp the screwdriver, but exactly how it might interact with various screws scattered nearby. Most remarkably, it accomplishes this feat having observed just one demonstration of screwdriver used weeks earlier, with a completely different tool. This isn't science fiction anymore. This is the reality emerging from today's research. To understand the significance of these advances, we need to recognize what computer science robotics truly represents. Traditional robotics focused on building the muscles and bones of machines, the mechanical systems that could move and manipulate objects. Computer science robotics, however, is all about creating the brain, the intelligent decision-making processes that transform mechanical systems into truly adaptive agents. Think of the difference between a player piano, which can only repeat pre-programmed melodies, and a jazz musician, who can improvise, adapt, and create entirely new music in response to their environment and fellow performers. This field represents the nervous system of modern automation. Computer science robotics sits at the fascinating intersection of artificial intelligence, control theory, computer vision, and machine learning. It creates systems that can perceive their surroundings, reason about complex scenarios, plan sequences of actions, and execute those plans while continuously adapting to changing conditions. The significance extends far beyond academic laboratories. As we approach widespread robotic integration into manufacturing, healthcare, logistics, domestic services, and autonomous transportation, the computational foundations developed in this field directly determine how effectively these systems can operate alongside humans and adapt to the unpredictable nature of real-world environments. The first dominant theme emerging from this research is affordance, understanding, and object interaction. Imagine you're in a foreign kitchen, trying to prepare a meal. Even though you've never seen these particular utensils before, you can quickly understand which objects might work as cutting tools, which containers could hold liquids, and how different items might work together. This intuitive understanding of what objects afford, what possibilities they offer for interaction, is exactly what researchers like Tian and colleagues are now teaching robots to develop. Their breakthrough demonstrates that robots can learn complex object-to-object relationships from just a single demonstration, achieving remarkable sample efficiency. The second and third major themes center on closed-loop control, with reactive planning and multimodal learning for generalization. Traditional robotics was like following a GPS route blindly, even when roads were blocked or conditions changed. Modern approaches are more like an experienced driver who constantly adjusts their route based on traffic, weather, and unexpected obstacles. Simultaneously, researchers are developing systems that combine multiple types of sensory input: vision, touch, language, learning from limited examples, and generalizing to novel situations. It's like training a chef who can not only follow recipes, but can also taste, smell, observe, and adapt, creating new dishes based on available ingredients and desired outcomes. The fourth theme focuses on energy efficiency and practical deployment considerations, while the fifth involves human-robot interaction and natural language integration. As robots transition from laboratory curiosities to real-world workhorses, questions of power consumption, computational efficiency, and long-term operation become paramount. Meanwhile, modern robotics increasingly concerns itself with how robots can understand and respond to human intentions, preferences, and instructions expressed in natural language. This represents a fundamental shift from programming robots through code to communicating with them through intuitive human interfaces. The sixth theme emphasizes perception and calibration for novel sensor modalities, particularly event-based cameras and other bio-inspired sensing systems. The findings from this research collection represent genuine breakthroughs that could reshape the entire field. First, researchers have demonstrated the feasibility of one-shot learning for complex spatial relationships, with robots learning object-to-object affordances from single demonstrations. Second, integrating model predictive control with learned value functions shows substantial improvements in grasping success rates, particularly in cluttered environments. Third, three-dimensional generative models enable realistic data augmentation, allowing robots to learn omnidirectional policies from single demonstrations. Fourth, hybrid communication protocols designed for robotic applications reduced missed deadline errors by over 90%. Finally, semantic keypoint representations enable robust manipulation of deformable objects by focusing on meaningful features rather than low-level geometric details. Let me take you deeper into one particular paper that exemplifies the revolutionary potential of current robotics research. The work titled O3AF ORD:1-shot 3D Object-to-Object Affordance Grounding for Generalizable Robotic Manipulation by Tongxuan Tian and colleagues represents a paradigm shift in how robots understand object interactions. Picture a child playing with blocks for the first time. After seeing just one demonstration of how a cylindrical block fits through a circular hole, they immediately understand how other cylindrical objects might interact with other circular openings, even if the sizes, colors, and materials are completely different. This intuitive leap from specific example to general principle is exactly what the O3AFFORD system achieves for robots dealing with complex manipulation tasks. The methodological approach in O3AFFORD is particularly innovative in its integration of complementary technologies. The system combines semantic features extracted from vision foundation models with detailed geometric understanding from point cloud representations. This dual representation allows the system to capture both high-level semantic relationships, like understanding that keys and locks are related objects, and precise geometric constraints that govern their physical interaction, such as the specific shape matching required for a key to turn in a lock. The one-shot learning pipeline represents the core technical contribution, enabling the system to predict affordances from single demonstrations rather than requiring extensive datasets for every possible object pair. What makes O3AFFORD even more remarkable is its integration with large language models. By connecting the three-dimensional affordance representation with language models, the system can generate natural language descriptions of object interactions and be guided by textual instructions. Imagine telling a robot, use the wrench to tighten the bolt, and having it understand not just what a wrench and bolt are, but how they should interact spatially and what forces should be applied. The experimental validation demonstrates substantial improvements over existing baselines in both accuracy and generalization capability, with particular strength in handling novel objects and categories not present in training data. The significance of O3AFFORD extends far beyond immediate technical contributions. By enabling robots to understand object-to-object affordances from minimal data, this research addresses one of the key bottlenecks in deploying robotic manipulation systems in real-world environments where objects and their interactions are diverse and constantly changing. The approach has immediate implications for manufacturing, where robots need to handle diverse parts and tools, household robotics, where objects vary widely in form and function, and any domain requiring flexible, adaptive manipulation. Most importantly, this work suggests a new paradigm for robot learning that moves away from collecting massive datasets towards systems that rapidly adapt and generalize from minimal examples. Looking toward the future, the research explored today reveals a field experiencing rapid evolution and increasing sophistication. Computer science robotics has moved beyond early paradigms of purely rule-based systems toward integrated multi-modal systems, combining classical control theory, modern machine learning, and advanced perception technologies. Think of the current state like a symphony orchestra finally learning to play together. Different sections have been developing independently, but now we're seeing these capabilities harmonize into systems greater than the sum of their parts. The integration of foundation models represents another major advancement, democratizing access to sophisticated robotic capabilities while addressing the simulation-to-reality gap that continues challenging the field. As we conclude today's exploration, several key insights emerge, painting an exciting picture of where computer science robotics is heading. We've seen how researchers are solving the sample efficiency problem through systems learning complex interactions from single demonstrations. The integration of foundation models gives robots access to vast repositories of human knowledge, while new methodologies bridge semantic understanding with physical manipulation requirements. These breakthrough findings represent fundamental shifts toward robots that rapidly adapt and generalize from minimal examples, evolving from narrow specialists toward integrated systems combining multiple types of intelligence and reasoning. The implications extend far beyond robotics itself, with potential to transform manufacturing, healthcare, domestic life, and countless other domains. The research we've explored today lays groundwork for a world where intelligent robots operate as collaborative partners, understanding, adapting, and contributing to human endeavors in ways we're only beginning to imagine. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from archive preprint server. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer: this video uses archive.org content under its API terms of use. AI Frontiers is not affiliated with or endorsed by archive.org.